Hello and welcome to another edition of Physics 264 Lab Preparation Shows. I'm Dr. Steve Brule. Today we're going to look at RC circuits and phase relationships in an RC circuit. It's a little redundant, isn't it? Well, let's see if we can get this show on the road. First of all, we're going to observe how current flows in an RC circuit by exploring an RC circuit with a battery and switch. We're going to learn why the voltage on the resistor is always in phase with the current in the circuit. We'll learn why the voltage on a capacitor always lags the resistor voltage by 90 degrees in an RC circuit. And we'll be surprised by the fact that the current put out by an AC source is not in phase with its own voltage when we have an RC circuit. Well, not always anyway. We'll get some practical tips about how we'll measure phase differences in RC circuits, and we'll be careful not to electrocute ourselves when we're using transformers in the lab. Well, here's a battery hooked up as a resistor. What does this say? Let's go away. I'm going to get this going over here. Sorry for that interruption, people at home. Here's a battery hooked up as a resistor and a single pole, single throw switch. Yep, no problem there. What sort of relationship do you expect between voltage and current? Well, I expect as soon as I close this switch, the current will just start flowing through R1. I'm a little bit less dexterous as normal because I'm using a different system here. And we can prove that by just using Ohm's law, V equals IR. I can switch the IR to RI, of course, and you'll see why I did that right now, because if I make voltage a function of time, then we've got this constant out in front of the current is a function of time because R is a constant, so that's why I brought that out in front. So if voltage is a function of time, or I would say if current is a function of time, then the voltage in the resistor is also a function of time, and it will be directly in phase. It's just a constant times the current is what the voltage is when we have a resistor. Remember that always, ladies and gentlemen. Well, let's hook up an oscilloscope and look at what the voltage across the resistor looks like. All right. Let's see if we can switch screens here really quick. And I have to open the first program, which is, I think, this one. There it is. I've got an oscilloscope set up across a resistor. There's channel A. I've got the negative terminal attached to the negative, or the ground, which is also the negative terminal of my battery. The battery's connected to the resistor using that switch. I use the key space closes that. And let's turn the system on, and we'll see what the voltage looks like. This is kind of anticlimactic. I close the switch, the current or the voltage goes right up. I open the switch, it goes right down. Close, open, close, open. So you see the current instantly starts going through the resistor as soon as I close that switch. Nothing surprising there. Let's turn off that and go back to our show. All right, but you'll see the reason why I did that and after our next little interlude, which shows you that that doesn't necessarily happen all the time. Let's add a capacitor to the circuit. There's a capacitor. And now I've got channel B of my oscilloscope. It's ground. The negative terminal to channel B is going to ground here. And so channel B is looking, it's viewing across C1, as you can see. And channel A, I've got the negative terminal on across R1. So now A is looking at the difference, the voltage drop. We could say the difference in voltage or the voltage drop across R1. But let me tell you something, that this would not work with a real oscilloscope, because a real oscilloscope, both of these negative terminals are connected together and they're already connected to the ground of the circuit. So you couldn't connect this circuit that I have that would look at the resistor and the capacitor at the same time. It's a shame. What you could do it, but you'd have to take Physics 264 and go all the way to the end of the course where you learn about op amps, and then you'd have to have a buffer here that you look or make it a difference amplifier. We'll learn how to do that later. Okay, and I just wanted to mention that this capacitor has a switch on it so that when I close that switch, it'll short out this capacitor and there'll be no charge on the capacitor, and it'll look just like there's a wire going from here to here, and we just have the battery going across the resistor again. So, and the reason I do that is so that I could cut the charge on the capacitor instantly and open it up again so we can see what the circuit looks like when I do that. Okay, let's go back into the land of multi-sim, and we'll get that one going. So I hope I can remember which one I want to open. RC, I think it must be this one. It's a little slow opening. There we are. I'm going to reverse that. As soon as I start that, I'm going to reverse that so we can see it in white. There we go. So the S1 is already closed. Oh, S1 is closed. It's open. It doesn't make any difference now because what am I looking at? Blue is the capacitor voltage. The capacitor is already charged up to the 10 volts. I believe that's, yeah, 10 volts down here. So it's already charged up to the 10 volts, and even when I open this switch, it stays charged to 10 volts because it's charged up. And multi-sim is very clever to know that the capacitor is still charged. So what I'm going to do is close that switch here, and now I've shorted that across, and then the voltage on the capacitor goes down to 0. What happened to the voltage on the resistor, I'm wondering? Why isn't that showing up? It should be in red because I have that red. So let's open that up again. And now I'll close switch 1. Oh yeah, now we see both of the voltages. And see what happened? I'll do that again now with the switch. I close the switch. The red is up, so now we're looking at all the voltage dropping across the resistor. No voltage is dropping across the capacitor. That's why we have 0 there. Close the switch. Open switch A, and then the voltage on the resistor is going down, as you see. The voltage on the capacitor going up. Let's watch that once again. I'm going to close, grounding the capacitor, so now it's just a resistor circuit, opening that circuit, and then the capacitor starts charging. That's the blue one charging up, and the voltage on the resistor is going down. It's dramatic, isn't it? Let's do it one more time. That's closed, so it's just like this resistor and a battery in the circuit. I open the switch, the capacitor starts charging, and the voltage on the resistor starts going down. Well, what that means to us, I'm going to do that one more time as I talk. What that means when the voltage on the resistor goes down, since the voltage on the resistor is directly proportional to the current in the circuit, then we know that when the voltage on the resistor is going down, the current in the circuit is going down. I'll do that one more time. There it is. As the capacitor charges up, the current in the circuit is going down. And the reason for that is the capacitor is charging up, and it eventually charges up. The blue eventually charges up to the 10 volts of the battery, and there's no more voltage drop across the resistor, so there's no reason for current to flow. All right, that was our point of that demonstration. Let's turn multi-sim off. We'll go back to our regularly scheduled show and see what else we have in store. Well, what did we learn from that? The voltage across the battery. Oh, I forgot to do that. I wanted to put the leads across the battery. Maybe you could just imagine what that would have been. If I had had my oscilloscope set up so that it looked at the voltage across the battery when this switch is closed and open, what do you think would happen when I close that switch and open it? Why don't you press pause and then come back? Well, welcome back. What would happen is, since the battery is a source of constant voltage, even when I have this switch closed, the battery maintains its voltage. Whether that switch is open or closed, it's only going to be 10 volts. But we see the voltage across the resistor and voltage across the capacitor are the ones that change. All right, let's see, what else did we learn? Current through a resistor is always the same as the current through the capacitor since they're in series. I didn't mention that in our show on the multi-sim, but if we've got current going that way, current's going to go through here because it's all a series circuit. We can't have any current through the resistor unless we have current through the capacitor. So we know that's true. Since there's no there's initially no charge on the capacitor. It has zero initial voltage. We did see that. And the resistor has all the voltage drops. So that's when when I had this closed, this initially had no voltage drop. So the whole voltage drop was across the resistor, which was 10 volts. And then as the capacitor charged up, then its voltage went up, and then this voltage went down to zero eventually when the capacitor was charged. As the capacitor charges, its voltage increases, and the voltage across, yeah, we just said that. That's Kirchhoff's law. It says that they're in series there. And since we know that the voltage on the resistor is directly proportional to the current in the circuit, we know the current is decreasing along with the voltage in the resistor. Even though we don't have a current meter in here measuring the current, I know that the current is directly proportional to the voltage across that resistor, so I don't even need to measure the current. I know that what the current is because it's directly proportional to the voltage on the resistor. And in fact, most of the times in real life, you don't use an ammeter in a circuit like this. You just put your leads across some resistor, measure the voltage across that resistor as a function of time, and then divide by the resistance. You've got the current. All right. What are we doing now? Okay, well, let's move away from just having a battery that we're closing a switch on an RC circuit. Why does that keep saying that? And we're going to put in an AC voltage source, or a power source that's AC, and it's going to create a current. We're going to say the current is a function of time, and it's some maximum amount times this cosine of omega t. And even though some people will say a cosine is not sinusoidal, but it is, folks. All right. So since we know that I is equal to this expression here, I max times the cosine of omega t, which is just a cosine wave, and then we just multiply R times I, and we've got V. So this is not velocity. Voltage as a function of time is just the resistance times the current that's moving in the circuit. The voltage. So that's the voltage across this resistor. So we just calculated, that's just IR here, but I is not capital I. We use a small I when the current is changing. Okay, well, how could we do the same thing for a capacitor? We know this is the definition of capacitance for a capacitor, and we'd like to know what the voltage is on the capacitor as a function of current. Well, I solve this equation here for voltage, just dividing both sides by 1 over C, and I see I've got voltage as a function of charge instead of current. Well, it's a little bit of a problem, but we're going to get over it. If I know what the charge is as a function of time, I know what the voltage is as a function of time on that capacitor. I just have to divide the charge by C at any instant, and I know what the voltage is across that capacitor. But now I have to figure out what is charge as a function of current. Well, the definition of current is the change in charge with time. You knew that from 161. And we can multiply both sides by dt. We can integrate both sides of what we've got left over there. And since we know that I, remember we're saying the current in the circuit is just some maximum value constant times cosine of omega t. So I put this in right here for the current. There's my dt. So now I integrate dq over here and get q. So now if I can just integrate this, I've got what q is. Well, the integral of a constant times a cosine is just that constant times the sine, but we have to divide by this constant because when we take the derivative of that, what's going to be the sine omega t times omega, so we had to have that one. Remember how to do that. Okay, so this is the solution to our problem. That's what charge is as a function of time. We just integrated that, and I'm going to plug this equation into that equation up there, and then we end up with an equation for the voltage on the capacitor as a function of time. And we see it's 1 over C, so that's a constant, times I max over omega, which is also a constant. That's just the angular velocity of the wave that we're driving the RC circuit with, and then it's times the sine of omega t instead of cosine. So here's our situation. We've got a AC voltage source, and we derive that the voltage across the resistor is going to be the resistance times this I max cosine omega t. That was just our current there. And then the voltage across the capacitor is going to be this constant term here times the sine of omega t. And you know what sine and cosine are. They are separated by 90 degrees. So here's the voltage on the sine wave is this one, and the cosine wave is this one. So if this is the voltage on the resistor, which goes by the cosine, then the voltage on the capacitor goes as a sine, and the sine is 90 degrees behind the cosine wave. So that's why we say that the voltage on a capacitor always lags the voltage on the resistor by 90 degrees. And that's at any angular velocity that we have here. No matter what omega is, we still have a cosine up here and we have a sine here, so they're always 90 degrees apart. Well, let's check that using multisim. And before we go into that, let me just mention that with multisim, I guess I am going to check that. I was a little ahead of myself there. So let's go into switch programs again. Go into multisim and see if we can load up the right one. AC, RC with scope. I think that's this one. Yeah. Okay. As soon as it's ready, there we go. So I'm going to turn that on. Oh, and it's too tiny to see, so I'm going to change and this is something we're going to be doing in lab, change the time scale so that I can actually see the wave. Oh, what's this? It's triggering terribly. Well, this is a nice example for you, and I'm going to turn this off and fix the trigger for you. So the trigger is not on. I must have opened the wrong one of these things I'd say. So I'm putting my trigger on the waveform coming out of this sine wave generator, and I'll put my trigger on automatic, and hopefully that should work. So let's try to run this again. No. What if I do normal? There we go. It's normal triggering. Okay, so I'm triggering fine. It's a little jiggity-jaggedy. I can adjust that a little bit, but I'm not going to worry about it. But look at this blue. The blue one is too small. The voltage on the capacitor is too small for me to actually see what's going on. So I'm going to go over to channel B, and I'm going to change my voltage scale until I can see that. So here's the red one. I can tell it's red because that lead is red. So that is the wave coming out of the signal generator, and then the voltage on the, it's not really the wave coming out of the signal generator because and this is what I wanted to point out, channel A is looking at the difference between this point right here and this point right here. Later on, in real life, we can't do this because oscilloscope's grounds are not floating like this, but multisim is a wonderful tool, and it allows us to do special things like float our grounds on an oscilloscope. So here, this oscilloscope is looking at the difference of voltage across the resistance, and then this channel B is looking at the voltage drop across the capacitor. So here's channel B, and that's 90 degrees behind the voltage on the resistor. Now, I know what you're thinking. You're thinking, I said the voltage was a cosine wave, because, but it's arbitrary whether we call it a cosine or a sine. If we'd gone through everything and called everything a sine, that'd be fine. But even if I can change this, let me see if I can get this going. So if I mess with my trigger, and I'm triggering off of A, and I go to my level, and I can change my level at which I'm triggering. So now I'm triggering, oh, Dr. Bruhl's getting a call. Let me turn that off. So I've got my trigger up at 15 volts. So it's triggering right there at 15. So this must be giving out 15. What happened? It stopped. Let me start it up again. Oh, I know what happened. The trigger didn't, it stopped triggering. My trigger was a little bit too high. So now it's triggering up at the top of the wave instead of down at 0. And then it looks like a cosine. Then this looks like the sine wave like we expected. I'm going to go back down just to dramatize that. So there I'm down to 1 volt. So now it's triggering at a voltage of 1 here. But see, these two waveforms are still 90 degrees apart. They're always 90 degrees apart, the voltage on the resistor and the capacitor. I'm going to go all the way down to 0. Oh, what's that? Oh, millivolts. It's now on millivolts. It's going to take me a year to go down to that. Let me see if I can type in 0. Yeah. So there it is. So now it's triggering right at 0. And oscilloscopes, just like in real life, oscilloscopes are a little bit finicky when you're triggering at 0. So just keep that in mind. Any questions? Okay, good. Well, let's move it right along then. I'll turn multi-sim off and we'll go back into the world of PowerPoint. This is working great, isn't it? How about the source voltage? This is a tough question. Is the source voltage in phase with the current it generates? So we just learned that the voltage on a resistor is 90 degrees ahead of the voltage across a capacitor. But where is the voltage on the signal generator, or the power supply there that we're calling an AC power source? Where is its voltage compared to the current that's going through the circuit? Why don't you press pause and see if you could figure that out? This is a tough question. Okay, well, let's see if we can understand that. So the voltage, I know this is VR, and this is VC. So if this voltage drop is VR and this voltage drop is VC, this must be VR plus VC by Kirchhoff's loop rule. So I'm just saying now I have a way to write a mathematical expression for the source voltage. It's just the resistor voltage is a function of time plus the capacitor voltage is a function of time. It has to be because it's all in a loop. Aren't you glad you learned that stuff on Kirchhoff's law? Okay, so there I just plugged in the equation for the voltage on the resistor that we derived. Here's the voltage on the capacitor that we derived, and that's our expression. I just took the I max out of both of these terms to show you that we've got two important constants. One is R, and the other one is 1 over omega C. Now, the phase of the voltage source is going to depend on the relative size of these two important constants. If the resistance is much over, so these are both in the same units. If you divide by 1 divided by omega C, that is in the same units as resistance. Amazing. So if the resistance is much higher than 1 over omega C, then this term is much larger than this term. We can just forget about that term, and we can say that the source voltage then is going to be the same as the resistor's voltage. It'll be that cosine wave, and the source voltage will be in phase with the resistor and out of phase with the capacitor. If, however, the resistance is much smaller than the 1 over omega C term, then we can ignore this term, and then the voltage of the source is going to be the same as the voltage across your capacitor. It's going to be the I max times this term. So that's the voltage of the source will look like this. It's fickle, that source voltage. And if R and 1 over omega C are both in the same neighborhood, so they don't have to be equal, but they're like roughly, one might be 0.5, the other one might be 0.7, or they're relatively close. Then the source voltage will be playing somewhere between these two. So then your source voltage is going to be something like this. Well, wouldn't that be neat to be able to simulate that? Well, unfortunately, Dr. Brule couldn't get multi-sim to do that because I needed a phase inverter on my, I needed to get the difference of this in a multi-channel scope. Yeah, because we wanted to look at we would need to look at this voltage on one channel of our scope. And Multisim has a 4-channel oscilloscope, which I've never seen one in real life, but I guess they exist. And I put that on one channel, and then I put the capacitor voltage on the other channel, and then I wanted to put the difference between these two voltages on the other channel. And with the multi-channel scope, they don't allow a floating ground for each input, unfortunately. You'd think in the fairy tale world of multisim, they would allow such a thing, but they didn't. But let's see what they did allow. We're going to go into one final... So here we are at our simulation, and we're going to simulate the voltage across the capacitor. And you can see we've got the oscilloscope channel B hooked up to measure the difference in capacitor voltage, just like we had before, where this is the ground and this is the capacitor voltage. So channel B, which is blue, is going to be the capacitor voltage. But now we've got the situation a little bit different. Now channel A is hooked to the output of my function generator directly, and that's how we had it before. But now, instead of looking at the difference between this point and this point, in which case we would be looking at the voltage across the resistor, we're going to look at the voltage across the entire distance, which is the voltage of the source. So when I run that, and you can already see what it's going to look like, these two waves are right on top of each other. So what does that mean? Does that mean that the voltage of the source is in phase with the resistor, or the voltage on the source is in phase with the capacitor voltage? Why don't you press pause and see if you can guess that? Well, it's the capacitor. Welcome back. It's when they're in phase like this. See, since the blue is the capacitor voltage and the red is right on top of the blue, see how they're right on top of each other there? Then that means they're perfectly in phase, and the voltage, so that means the voltage of the source is in phase with the capacitor. But then watch what happens as we increase the frequency of our generator over here. Let's go up. What do you think? We were at 1. Let's go up to 3. They're still right up on top of each other. So it's not, they're a little bit off, but I'm going to go a little bit farther now away. Let's take it up to 6 hertz. Oh, they're still on top of each other. This is exciting. Will we ever get them off? Let's go up to 60 hertz. That'll show it. Now I can't even tell. So now what we have to do is change our time base. So let's, oh, and there it is. So there's the capacitor voltage lagging the, and this is the source voltage. So before we had this was the resistor voltage and this was the capacitor voltage, and they were always at 90 degrees. And now this is, I can tell this is not quite a quarter of a wave. Quarter of a wave would be this far, so it's not even close to a quarter. So it's just, the blue one, which is the capacitor voltage, is lagging the source voltage by an angle of about, looks like even less than 45 degrees. So even less than half of a quarter. So that would be an eighth for those of you who have a calculator at home. So let's see if we go up even higher, that's going to shift over to 90 degrees. So let's do that and really see what we can get out of this simulation. So instead of 60 degrees, 60 hertz, let's go to 600. I know I'm going to be up there to where it's going to be all the way over to the resist. So this is going to be 90 degrees out of phase. Well, let's see if it is. Again, it's, and this is going to happen to you in lab too. So let's fix the time frame so that we've got about 1 wave. That's nice. And then I'm going to make the blue one a little bit bigger because I need to see it. There we go. So now you can see that here's where the 0 point of the source voltage is, and then here's where the 0 point of the capacitor voltage is, and it's almost exactly 1/4. So it's not even quite there yet, though. So it's not quite to 90 degrees yet. So if I increase the frequency here even more, I'd get this to move over a little bit. So see how the source voltage is? It's phase changed relative to the voltage across the capacitor. And remember, the voltage on the resistor was always 90 degrees ahead of here. So the voltage on the resistor would be virtually the same at this point as the voltage of the source, because it's 90 degrees ahead. Well, I won't do this anymore, and if you want to see it again, you can play back that exciting part of this show. Right now, it's time for us to go into what's happening in lab this week. Well, we're going to set up an RC circuit on a breadboard, and here's a capacitor right here. Here's a resistor, and we see how they're connected right here at the center. And this end of the capacitor is hooked to this terminal right here, which is going to be ground. Oh, and notice that we're not hooking this up this week because we don't need any DC power supply. We'll connect this end over here to the ground of our circuit, just like in our circuit that we want to simulate. These 2 points are connected like I already showed you. This side of the resistor is going to the other terminal, so then we can connect that to our AC power supply. So there's the red one coming out of here is the hot, that's what's giving the power supply, and then there's the ground of the power supply, and it's hooked to the ground of, or what we're calling the ground, which is that side of that capacitor right here. Okay, I hooked channel 1, you don't have to do this, but I hooked channel 1 up to the source voltage, so it's right on top of here. It's not going through here, but it's like, here's the lead that's coming out of this guy, and I've got it right on top of the lead coming out of the AC power source. So, and the ground of the oscilloscope is hooked into this ground. So this oscilloscope is hooked directly to the output of the AC generator, just like you had in the last exciting multi-sim demonstration. If it so happens that your waveform is somehow like off center, what you do is you ground your input right there. You put the input to ground, and then you adjust the position using this knob, as Michael is demonstrating here. And then you see here, Michael has adjusted this knob, even though he's pointing to this one now. He adjusted that knob so that that line went down to here. And once you get that, your channel zeroed, you can DC couple it again and look at your signal. And here I've done the trigger. Remember all that triggering problem we had in multisim? Well, I made the source of my trigger to be channel 1, and this is where you adjust the level of the trigger. So if you want it to look like a cosine, you can move this knob back and forth until you're triggering at just the voltage you want to. And I've got the coupling automatic, and I'll tell you, you might have to fiddle with this, and either normal or automatic. I don't know what the difference is, but sometimes it works on one and not the other, and sometimes it's the other way around. If you had your source to channel 2, you could trigger off of your signal in channel 2. If you had it set to line, that means it's triggering at 60 hertz a second. I don't know why you'd ever want to do that, but if you were looking at something that it was something to do with the source in the wall. And then this is if you have some external trigger you want to put into your oscilloscope, but we probably won't ever use that. Okay, well, look at this waveform. It's cut off just like in multisim. What do? You adjust this knob, you adjust this knob until it gets to be in range. And look at that sharp edge up there. That means that the function generator that we have is not giving a very good sine wave because it's got this little edge on the end. And normally that's not going to cause us a problem, but that is a bit of a distortion, and sometimes it'll come up and if you're amplifying or something. Okay. Oh, look how I coiled my wire. Do you wonder why I did that? Well, you'll see in the next picture, because when we put channel 2 on here, so here's channel 2 coming around here, which I've also coiled that up, and then you can follow its wire, and it's going into this terminal, which is hooked to a green wire, which is connected to the junction between the capacitor and the resistor. So now that channel 2 is going to be on measuring the voltage across the capacitor, see? And it's sharing the ground from channel 2 is coming in here, and it's into this little tree, and all those are sharing a common ground, and that's very common in electronics land. So now you see why we want to coil our wires and keep everything tidy, because I'll tell you what'll happen, and it's happened to me and it happens to students all the time, is they don't coil up the wires, they're not tidy, and then they never know what channel is looking at what, and you get all confused and you have to start all over. So it's best to just keep everything neat from the beginning. Well, just like in multisim, if you've got too many waves on here, you can't really measure the phase of this. It's too small. So you adjust the time per division, just like we did in multisim, but we had to put a number in there. This is a different way to do it. You use that knob until you get about one wave that's fitting on. Look, see how this wave is starting and it's not quite all the way up there? You can adjust that with the horizontal position. Where's the horizontal position? There it is. So with this knob up here, if you wanted to move everything on your screen to the left, you just turn that over this way until, and that's handy sometimes because maybe you want to have this point of your wave be exactly at that point of the grid. So it perfectly intersects one of your grid lines, and then it's easier to measure this distance. So that's a handy, you'll use that. Okay, you may have to adjust the volt per, okay, so just like we did in multisim, the voltage on the capacitor is going to change at different frequencies, so you might have to boost that up or lower it down to make it so it fits right. Well, how do you calculate phase? It's just this distance right here. That is the phase right there, but that's phase in time because this is the time axis on your oscilloscope. That's measuring in, it's 50 microseconds per division in this particular setting. And the setting is done over, well, you saw where it was before. So that means that's 50 microseconds, that's 50 microseconds. So if that's 50, there's 50, looks like about 50, 60, 70, 80. It's about 80 microseconds right there. So that yellow line right there, of course, this yellow line that I'm now writing all over, that is your phase, and the phase difference is about 80 microseconds, 1.6 divisions times 50 microseconds. Well, how do we calculate the phase angle? It's the phase difference divided by the wavelength of either one of those waves. So I pick this particular wave right here. And its period is this. I said wavelength, but it's really the period, but your measure, it looks like wavelength. So this is the period, and that looks like 1, 2, 3, 4, 5, 6, 7.2 divisions times 50 microseconds per division. So that's another time. So you're dividing the phase in time by the period in time, and then that's the fraction of a wavelength that is the phase difference. You multiply by 360 degrees to get the phase angle. You probably know that from your trig course. Okay, and that's the end of that. So we just had one more thing to talk about today. We're going to be looking at the sinusoid. One of the things that we're going to do in lab this week, because it's so short and fun, we added an extra thing. And this is a step-down transformer. It's a pretty big transformer, isn't it? Could carry quite a bit of current, I think. And one end of this, there he is, that Michael's holding the end that plugs into the wall, and the other end is these other terminals are going to come out, and they're lower voltages because it's a step-down transformer. And you're plugging this into the wall, so it's a little dangerous. So what we're going to do is you don't plug it. First of all, you start off by not having it plugged in, and you take the leads that are coming off of your transformer, there'll be 3 of them, and plug them into your breadboard to keep them from flopping around. And if they touched, it would be bad. It could cause it to catch fire and things, and you don't want to touch it yourself. The voltage is not that high, but it's still, you don't want to, it's a good practice not to touch those. Okay, so we've got those 3 wires in our breadboard, and then I see that Michael has got his voltmeter here hooked up. I think that's in the next, no, it's not. So the voltmeter leads are coming around and going into here. There's one end of the voltmeter, here's the other one. So one end of his voltmeter is on this terminal, the other end of his voltmeter is in the middle terminal. So he's measuring the voltage across the center tap of my transformer in one end of the transformer. And then he's going to pick this middle one up and measure it across the 2 ends of the transformer, and he'll probably pick this one up and go to the center again. And that's the end of, oh, and then you'll leave this in there, unplug it, and then plug your oscilloscope, take the leads of your oscilloscope instead of the, I wish I could erase, instead of having the voltmeter here, we'll have the oscilloscope hooked up, and then you'll look at what the waveform looks like that is being generated by our power company and see how close it is to a perfect sine wave. And I believe that's the end of our show. Remember to keep the transformer unplugged until it's all hooked up. And then once you plug it in, don't touch any of these exposed 1942 terminals that would not be good if you touch. Yeah. Okay, what do? We did all these things. I'll let you go through them on your own so we can get through this a little quicker. Thanks for coming in today, and I'll see you on Thursday. So how do I stop? Camtasia. 52 minutes.